So, or all of you are trying to be good students and you don't want homeworks. Okay, that settles that. Um, anyway, right. So we'll get started today with a slightly different type of binder, uh, and we'll build on this. Small change in the program for the day. We were initially planning a demo of printing, right? That was to be in the afternoon. We may change that because tomorrow we have a field visit where we will see live printing demo anyway. So today instead we will go to the site of a bridge, the 3D printed bridge in the afternoon. So this will be after the quiz. So only if you take the quiz are you allowed to come on that tour for the bridge. Okay, right. So far we have started off in a gentle way where the first session was probably all fluff, where we talked about additive manufacturing, all things good about additive manufacturing, then went into 3D printing. We started getting into rheology, right? Scratch the surface on rheology. Please remember that whatever topic we are covering here is basically just giving you enough information to make you dangerous. Okay? Because they say half knowledge is dangerous. So we are making you dangerous. If you really want to get in-depth information on any of these topics that you cover, there's a lot to study, lot to understand. Most of it will be available in the form of papers. We'll be happy to share with you. If any of you is interested, please to write to us. We'll make sure that we get those papers to you, right? Books in this topic are still not available, certainly not for printing or extrusion-based printing, to be more precise. There are a few reports that have been put out by agencies like RILEM or associations like RILEM. RILEM has just conducted a round-robin test. I know there was a question yesterday. So there's a massive round-robin test series that was conducted by RILEM. There were 38 labs that participated in this worldwide. All labs except any from US, which is completely missing in action. That's because ACI is taking up a parallel effort. American Concrete Institute is taking up a parallel effort of doing round-robin testing. And basically, the outcome of these round-robin testings is to, at some level, normalize what we would call properties. Right now, with perhaps 150 years of documented literature on concrete, when we say strength, we understand, we know how to use the strength that we get from a small cube or a cylinder and translate it into a structural capacity of a concrete structure. We've come to that point. Now we're comfortable with it, right? We have, over the years, learned from our mistakes in design, where perhaps some structures collapsed, some deteriorated. That has led to tightening of the codes, where we have actually improved on our codes. But that has been the accumulated knowledge that has come over the years. Now, this is still a nascent field. So I know a lot of you have had a lot of questions. You've asked me these questions as to, oh, how about this? Well, it'll happen in due course. We are not there yet. At this point of time, we are just looking at the technology and perfecting the technology to deliver what we want. Now, there's still this question, and this will be covered in subsequent lectures, is how do we take something that comes from material test, right, and translate it into a structural design? That is still a missing gap, and people are working on it actively. Okay. Now, that being said, whenever we come up with a new technology, we always say, what I want is a one-size-fits-all. You basically give me something that is green, sustainable, and you name it, it should all be ticked under this new thing that is, otherwise we will not adopt it. And this is one of those things that basically is a step in that direction. But people have been looking at alkali activated materials, okay, as alternate binders to cement. So there's absolutely no clinker involved in this, right? The hope is that these are greener binders. Okay, how green, we are still to establish. How sustainable, we are still to establish all of these things. But because the starting point, the material part of it, the alkali activated materials, they're also called AAMs to be precise. Okay, How sustainable, how green, those numbers are still being worked out. Now, let me get into the... So, first thing, what is an alkali activated binder? And what I need is an aluminosilicate source, something that has alumina in it and silica in it. Usually we start with GGBS or fly ash. Sometimes even metakaolin is used. There are other silica sources too. And what these materials bring into the picture is they contain calcium oxide. Some do, which is GGBS would contain calcium oxide. Fly ash is typically deficient in calcium oxide. But both of these typically contain silica and alumina, and that's what we're primarily looking at. And we activate these materials with an alkali silicate activator. We use an alkali, sodium hydroxide, that basically creates a high pH environment. And the high pH is required to dissolve the glass in these two materials so that it would release the silica and alumina, which I can then use to form binders from it. Now, we may use sodium silicate, we may not use sodium silicate. Right? The idea of using sodium silicate, which is also called water glass, is to supplement the silica that's available in these two materials. You basically, it's oftentimes the silica available is not sufficient for the formation of the binder. So that basically comes from the sodium silicate, which is typically added in a solution form. Right? Now, what is the outcome of this process? Well, there are, if I use either a fly ash or a slag, I would form one of these two binders here. That is calcium aluminosilicate hydrate or sodium aluminosilicate. It's not a hydrate, it's a misnomer. But somehow this name NASH has stuck because of a fortunate or an unfortunate accident that happened in a committee. And that name has since persisted. So, but at the outset, I want to clarify one thing. People use this term geopolymers rather loosely. Now, what are geopolymers? Geopolymers, by the strictest definition, are these sodium aluminosilicates. Okay. Now, when you start forming calcium aluminosilicate, when does calcium aluminosilicate hydrate or CASH form? When you start with a calcium-rich source, like say GGBS. Okay, and you were to alkali activate it, what you may form is a CASH. Okay, now CASH is like a distant cousin of CSH. Okay, therefore calling it a geopolymer is a misnomer, right? So please be careful. And I know people use it colloquially and it's rather a catchy word. So everybody throws around the term geopolymer, but not all alkali activated materials produce geopolymers. Okay. Now, if you really want a geopolymer, you should basically drop a source that has calcium in it. Right? You go with a calcium deficient source. Therefore, when you use only fly ash to activate with sodium hydroxide sodium silicate, you produce sodium aluminosilicate hydrate, NASH. That, in a technically true sense, is a geopolymer. Okay. So now the more accepted terminology is AAM. We just call them alkali activated materials. Okay. Just to avoid the confusion. Now, you looked at a similar figure for cement paste. Right? What did we, when we looked at cement paste or concrete made with cement paste, we drew a line. We said, well, everything that is not aggregate goes into the paste, right? Now, if I look at a concrete made with an alkali activated fly ash slag binder, which is an alkali activated material, I would have a binder paste, which is my fluid medium, and I'll have aggregate. And just like before, aggregate, the two things that are of concern to me are the aggregate content and the packing, right? Now, whatever I choose to do packing for, you've had a whole exercise yesterday. Whatever the objective of packing will still remain the same here. Nothing changes as far as that goes. But this binder fellow here is much, much more complicated. It is not as straightforward as what we did with cement paste. Why? Because if you look at cement paste, what are the variables that I have? If you think about it, there's only fundamentally one variable, water to cement ratio, right? Here, it is not limited to that, right? Here, what I could have is the binder source material itself could be a combination of slag or fly ash, where I could have 100% slag or 100% fly ash, or a combination of these two. So that's the first variable. The second variable is the composition of the activating solution. Now, what is the composition of the activating solution? I will have the molarity of sodium hydroxide that is in the solution. That is one of the variables. We have this ratio. Actually, the reverse of this is usually prescribed. The silica to sodium ratio in the solution. That's also called MS. Okay, so the MS is the other ratio, and the silica content in the solution. How much dissolved silica or soluble silica do you have present in the solution? So basically, now the variables that I have are quite a few that I have to handle. Okay, and each one of these has an impact on the rheology of the paste. Remember, what controls the fluidity of the concrete is the rheology of this fellow. That is the primary variable. Of course, the other variables also come in, but this is the fundamental thing that controls the rheology of the concrete made with this binder paste. So my variables now have really skyrocketed. If you think about it, I have the ratio of these two materials, the solution composition. I have three variables to track. And to make things worse, the equivalent of water to cement ratio is the solution to binder ratio. How much solution do I mix with the binder material? That is the equivalent of the water to cement ratio. So that's also there, right? So now my variables really shoot through the sky when I start looking at alkali activated binder paste. Now, the first thing is, why do we add this sodium silicate? Like I said, and what does sodium silicate bring into the picture? Well, sodium silicate, if you look at fly ash and slag, these are my source materials. They're bringing in silica, but there's not adequate silica. So to supplement it, I add sodium silicate. Now, what happens when I increase the silicate content? What is silicate content? It's the amount of silica present in the solution made up of these two. Right? If I increase the silica content, typically my strength starts shooting up because I'm basically bringing in more silica that helps formation of either cast or gnash, and that leads to strength improvement. So having silica in the solution is almost a must if you really want a good strength from the material. Okay, only in rare cases where we are dealing with only slag, sometimes we drop sodium silicate. Otherwise, typically almost always you'll have to have that. And when you do that, then basically this proportion of these two matters, how much water I add, that controls the molarity, and the percentage weight of this to these two is another variable that I have to worry about. Now, coming to the rheology, going back to the basics again. So, if we do the rheology, and we'll stick to the standard test, a constant shear rate test, and yesterday you saw how to measure thixotropy. What we would do is basically do a ramp up. So we are ramping up in strain rate. Hold the ramp or hold the strain rate constant for some time. What do we hope to achieve here? Basically smash the internal structure, complete whatever deflocculation we can achieve, we try to do that, and then ramp down and see what state we are left with. What do I expect to get when I do the ramp up? Because this has, if it has a yield stress, it will basically start flowing only after I overcome this, a shear thinning liquid. This is during the equilibrium part where I'm holding the strain rate constant. What happens here? The structure breaks down. So what happens? The stress resistance, that basically starts decreasing, right? And then when I ramp down, I basically come down here, and usually the ramp down is a Bingham plastic. This is what we get for cement paste. But if you look at what I get for these materials, here I'm doing a slightly different test where I'm doing a ramp up and a ramp down. This was also discussed yesterday using a vane setup. So this is what you typically get for cement. You see, you get this is during the ramp up and this is during the ramp down, and it's a pretty steep ramp down, and it's a very straight line. So basically this is a very good approximation of Bingham plastic, right? You've already seen Bingham plastic. So if you look at the ramp down curve here, look, it's pretty straight. And if you project it back, there's a little bit of nonlinearity here, but that's something that we can ignore. So when you look at cement paste doing the ramp up and ramp down experiment, it basically behaves like a Bingham plastic. But if I take one of these alkali activated materials where I have 50% fly ash and 50% slag, and I'm taking a solution to binder ratio 0.39. That is, I'm adding 60 or 61% of this is the solids, which is fly ash and slag, taken in a proportion of 50-50, and 39% of the paste is activating solution. What is the activating solution made up of? Well, it is a combination of sodium hydroxide and sodium silicate, such that I get a silica content which is about 0.09. That means 9% of the solution is dissolved silica. Okay. Now, what do we notice from the alkali activated material? Well, you see, this is a ramp up curve and this is a ramp down curve, right? The ramp down is fairly linear, except you see what happens here, right? It doesn't go sharply to zero to our intercept here. Instead, it kind of tapers, and probably goes almost to a zero yield stress, right? So this kind of behavior, if you look at it, which basically comes down here and doesn't have a sharp intercept like what you see for cement paste, is what we call the Herschel-Bulkley kind of a behavior. Okay, Herschel-Bulkley is basically a broader term that's used to describe even the Bingham plastic. Bingham plastic is subsumed in the Herschel-Bulkley. Why? Because if this nonlinear portion here were to essentially become steeper, you end up with a Bingham plastic. Okay, so it's just a fine point to note here that most alkali activated materials have what we call a Herschel-Bulkley type of behavior. And what is more important is we identify the slope of this line with plastic viscosity. We've already seen this in the last lecture. What we see is on an average, if you look at the slope here, which is for cement paste, and the slope here, and mind you, these two have almost similar solids concentration. How do I identify the solids concentration? Well, here the water to cement ratio is 0.4. Here the solution to binder is 0.39. So they're almost comparable, right? Now look at the difference in the plastic viscosity. Now, typically my alkali activated materials will be much more viscous. That's something I have to prepare. What are the consequences of this? If I am to pump this material, right, what does the pumping pressure depend upon? The viscosity. So expect that this fellow will be physically, when you look at it, it's going to be stickier. Okay, it's going to be much tougher to pump. Your pumping pressures will go up. It doesn't want to flow, basically. If you induce flow, then it doesn't want to flow. Okay, the reason is it has a very high plastic viscosity. This is something that we have to contend with. Now, there's also something very interesting about silica. When you actually add silica into water, its state and shape depends upon two things. And one of the primary variables that controls the shape and the state it's present in is the MS. Okay, this is silica to sodium ratio in the solution. Where do I get this from? My activating solution is a combination of sodium hydroxide and sodium silicate. Sodium silicate brings in the silica, right? And the sodium hydroxide and the sodium silicate bring in the Na2O, right? So in the activating solution, I get this ratio forming there, the silica to sodium ratio, right? And we call this the molar ratio or the silica ratio. There are different terms that are used. But in the short form, we typically just call it MS. Okay. Now, this is the viscosity of a solution for different silica contents. So each of these lines is for different silica contents. Okay. Now, if I take a line like this, this has 46% by weight of the solution in dissolved silica. Okay. Whereas this, by the time you come down here, has 30% of the total weight of the solution in dissolved silica. Okay. Now, you may be wondering, why would I want to dissolve silica in a solution? Well, if you look at most commercial solutions, including paints, all of those contain dissolved silica. Okay. Now, and it is needed or it's used typically as a viscosity regulator in a lot of these applications, including some cough syrups. Okay. So, basically, what do I use silica for? For regulating the viscosity, right? Now, once I decide on a certain silica content, if I vary the MS, right, notice what happens to the viscosity. The viscosity first decreases and then it increases. Okay. The reason that happens is when the MS is very low, basically silica exists in monomeric forms. Basically, it is very close to monomeric or dimeric forms. It has not polymerized yet. Okay. As I start increasing the MS, which means basically the silica, proportion of silica relative to sodium, when that starts increasing, silica starts getting polymerized. So this is what I would get when it is highly polymerized. And the more it polymerizes, the more viscous it gets. Okay, so initially what's happening is that basically you start with very lot of monomers. So you have lot of particles which are, and this is a TEM image of silica which with a very low MS. So you get a lot of individual particles. So why does the viscosity decrease? At some point, these particles start coming together and starting forming dimers. So the volume of space that they're occupying within the liquid, that starts decreasing. So what you see is the viscosity decreases, hits a minimum and then shoots off. When it starts shooting off, that means it's starting to polymerize. Okay, so this viscosity of the activating solution itself now depends upon this MS of the solution. Okay, now I've added another complication to the whole story. Remember, I'm going to take this activating solution and mix it with fly ash or slag or a combination of the two. Now, just to give you an idea, typically, when you look at sodium silicate, it is much, much more viscous compared to water. Okay, the numbers that we get, and this we are being very generous here, this is at a very low concentration of sodium silicate. Okay, once you start getting into higher concentration, suppose I was to take 30% solids, you'd see that your number here would be actually around 1. If you start increasing the silica concentration, the lowest number itself would be 5 or 6 Pascal seconds, poise, right? Water is just 1 centipoise, 100th of that. So I'm dealing with a liquid that is much, much more viscous than water. Its viscosity is also not constant. How does this compare with cement paste? My water was of a constant viscosity. This didn't change. Okay, so I was left to handle whatever came with the cement paste that I could deal with. Here my problem is that depending on the composition, my viscosity of the solution itself will change, and then I have all the other variables that I have to contend with. Right. Now, what is the consequence of this solution? Well, we're doing a constant strain rate experiment, and if I say take fly ash and slag, now look at the proportion we're using. So we're using 90% fly ash, 10% slag. Again, it's an alkali activated material. I have fly ash and slag. We are basically combining it with an activating solution which has 3 molar sodium hydroxide. Okay, and the solution to binder is around 0.39, roughly about equivalent to cement to water, water to cement ratio 0.4. Now, what we are doing in this experiment is increasing the silica content. So what are we doing? We are actually dosing more and more silica into the solution. See what happens. When the silica content is 0, which means basically I am just adding sodium hydroxide to the paste, you get something that we are all used to seeing. Basically, the stress builds up. This is the yield stress. Then you get flow here. Right? Why do I call it a flow? Look at this. The resistance here has become a constant. I've sheared it off and now it's flowing at a constant resistance. Right? Look what happens when I add some silica. The yield stress actually decreases. Okay. So what is silica doing? Silica is actually at some level decreasing the viscosity, but doesn't stop there. Look what happens when I add more silica. It bounces back. So why do you think that happens? The trough is playing a role. Okay, so when you start adding more and more silica, at some point you will shoot up here, and the viscosity of the solution increases, and that actually increases the stress, the resistance that I get. So that you see here in the resistance. But something more fundamentally different happens. Something fundamentally changes. Look at the shape of this curve. It actually goes up, reaches a peak, and then it starts flowing. Look at the shape of this curve. It's fundamentally different. What is different? It actually builds up to the peak and then becomes a constant. Okay. Now, it took us a while to understand what is happening here. And the fact that this doesn't conform to this, that means this doesn't even look like this. Something fundamentally has changed. We look at this curve, what happens? It builds up to the peak and then it shears off here. Then it starts to flow, but then there's basically like a decrease after this point, right? That's not happening here. What's happening? The resistance builds up to a constant value and it stays at a constant value, right? So this, when we started looking at this, we said that, well, this actually behaves like what we call a Maxwell flow behavior. And I'll explain this to you in the next slide. Whereas this is what we call the classical yield type behavior. Okay. Now, when we start dosing silica, more and more silica into the solution, the fundamental flow behavior changes. It goes from what we call a yield type behavior to a Maxwell flow. Okay. Now, what is Maxwell flow and how is it different? Yeah, yeah, yeah. Sorry? Sodium silicate. Sodium silicate, I would be adding more silicate. Okay. And that's how I increase my silica concentration in the solution. Okay. Right. So if I do this constant strain rate experiment again, so this is what we said is a yield type behavior. I go from step 1 to step 2. This is where the material yields, and then it starts to flow. But look at what happens in the Maxwell behavior. The resistance continuously builds up to the peak and then it stays constant. Now, if I was to idealize the yield type behavior, this is how we would idealize this. Basically, you would use a Kelvin type of a model where you have a dash spot in series with a spring and then a spring that is shunted in parallel with this. So what happens if I pull this setup here? At some point, this spring breaks and then it continues to flow, right? This initial spring that you have here represents that percolated network that I have here that is giving that resistance. And once I shear it off, then it starts to flow, because if you look at it, suppose this spring were to break and I was to pull on it, what would happen? The viscous damper and the spring are the only two mechanisms that are giving me resistance. Primarily, the resistance is coming from the viscous part, which is nothing but this resistance here, right? So that is what we call a Kelvin model typically of a viscoelastic solid, right, which flows if this spring were to break. And breaking of the spring is basically my peak here. That is the maximum resistance that I get. What about the Maxwell flow behavior? What's the way I would show a Maxwell is that this parallel spring is not present. Okay, so when I start pulling on it, basically the resistance that I get is purely from the spring and dashpot. It continues to open and then it eventually continues to open once you get into that constant velocity regime. Okay, so this is like an idealized representation of a Maxwell behavior. Here, what happens? The resistance increases to a peak and then it stays constant. It's continuously deforming, basically. It doesn't rest. So what would happen if you had a material that has a yield type resistance? If a material has a yield type resistance, if you apply a small enough stress, what would happen? It would deform and come to rest, because it is basically this spring that you have here that is taking the load. It will arrest further movement, right? And unless you break this spring, it will not flow, right? But what happens with this kind of a Maxwell type of response? It will continuously deform. Look at the spring and dashpot arrangement we have here. It will continue to deform, right? So what is the dangerous thing about something that exhibits a Maxwell flow behavior? If you apply a stress and you leave it there, it will continue to deform. Okay. And that becomes very tricky for us to handle, because remember, one of our requirements in printing is shape retention. Now, and not just shape retention, buildability. We've had enough of that. How do we test buildability? I print a layer, I stack layers on top. Now, if this layer is going to continue to deform, then I'm in trouble. Okay, here what am I banking on? I'm banking on the spring. It will deform and get arrested there. That spring will take the load. It will not deform anymore. Okay, here I don't have that. It will continue to deform. And I'll show you what happens when we, and the reason for that is when we add more and more silica into the solution, what we measure typically is the state of flocculation. How much are particles flocculated? And we measure this thing called the zeta potential. A zeta potential is basically something that will tell you how likely is it that these particles will agglomerate. If the zeta potential is negative, more and more negative, that means you will see particles in an individually dispersed state. Whereas if the zeta potential starts going towards zero, the chances of flocculation is very high. Okay, so suppose I take cement, put it in water, and I measure the zeta potential. And if I measure a very high negative zeta potential, that means individual cement grains will be floating around as individual grains. But if the zeta potential is low or close to zero, then what will happen? The tendency for the cement grains to agglomerate is very high. Okay, so what does a surfactant do when you put it into a solution? It basically lowers the zeta potential. That's another way of looking to say that, look, I'm dispersing the cement particles. That's for cement. Now, what happens when I actually increase the silica content in these solutions? I find that the zeta potential, which I measure for fly ash or slag that is put in that solution which contains silica, that zeta potential becomes more negative. That means these particles tend to separate out, and that is where I get into this problem. And the issue there then is that if I look at individual particles of, let's say, fly ash, and this is actually a very good approximation for fly ash, because fly ash particles, yesterday we had this discussion, are very nearly spherical, right? They get coated with this solution. Now remember, this solution is not water. This solution here is that activating solution, sodium hydroxide and sodium silicate combination. And when we have these particles, which are, let's say, fly ash, coated with the solution of sodium hydroxide and sodium silicate, basically the same shearing type action takes place whenever these particles even are to come to rest. What would happen now? This fluid which is in this gap here is going to continuously deform. We just saw that. So what will happen? It will basically continue to deform and lose its shape. It will continue to flow. And this is one of the first problems we encountered when we were looking at alkali activated materials. Let me show you how the rheological behavior of this alkali activated material looks like. So here what we're doing is taking fly ash and slag 50 to 50. Solution to binder is 0.35, 3 molar sodium hydroxide and 0.9% silica content. This is the composition of the activating solution. This is the mass proportion of solution and binder. So basically this is equivalent to water to cement ratio of 0.335. Sorry. My binder is made up of fly ash and slag in 50-50 mass proportions. Now, I'm doing a constant strain rate experiment. So basically, I'm shearing it off. When I shear it off fast, look what you get. You get a yield type behavior. Look at this. It basically builds up very quickly to the peak and then it decreases, right? What happens when I slow down the rate? So when I start slowing down the rate, you see what happens? What's happening? Is here, when you go to a very slow rate like 0.001 radians per second, so I'm basically turning the spindle at a very low rate, what's happening? You see that the resistance slowly builds up. Okay, why is that happening? So what is the fundamental difference between these three curves? It's the rate at which I'm loading, right? Which means the viscosity, the viscous solution that I'm dealing with, the activating solution, that dominates. It tells me how it is going to deform. If I load it fast, I'll get a yield type response. Okay. If I load it slowly, I'll get a Maxwell type response. This is more like a Maxwell type response. What happens in a Maxwell type response? It will continue to deform. Okay. Now, other interesting things that start to happen. Suppose I look at an alkali activated paste with a solution to binder ratio of 0.385 and I increase the silica content in there. Okay. I'm basically keeping this constant, the solution to binder. It's like keeping the water to cement ratio constant, changing the composition of the water or the activating solution. And how am I changing it? By increasing the silica content. Okay. Look what happens here. So I'm showing you here data from two different pastes, one fly ash and slag in 90-10 proportion, another fly ash and slag in 50-50 proportion. But you notice what happens when I increase the silica content. Here, initially I get a yield type response, and then as I increase the silica content, it becomes a Maxwell type response. The peak resistance continues to increase. Okay, so what happens then? Whatever I'm getting as the peak resistance, what it's building up to, that resistance is increasing, but it's a Maxwell type response. It will continue to deform. Okay, and the same thing happens for both of these, which means that is basically, it really doesn't depend so much. Yeah, absolute values may vary, but it really doesn't depend upon the composition of the binder that I'm using. And notice what happens when I increase the silica content to the viscosity of the paste. Okay, the viscosity just shoots up. Right? As it is, I'm dealing with a viscous solution. If I add more silica to it, what will happen? It will only make the paste more and more viscous. Okay. If I add more silica to the solution, I'll transform from something that may have a yield type behavior to a Maxwell type behavior. Yeah. Sorry? Yeah. See, if you hold the stress constant, it will continue to deform. I'll just show you that. Okay. So when you're doing these rheological experiments like I've shown you here, we are applying a constant strain rate. We are not pausing anywhere. But suppose I was to pause it here, right? You'll see that it will continue to deform slowly. Okay. So that is what we notice typically in these Maxwell type responses. Okay. The other issue that we have with this is this. Now, you've had this class on thixotropy. How do we measure thixotropy? We basically ramp it up, hold it constant, ramp it down, and take a small break, and then do a ramp up, ramp down, right? So what we're showing you here is the first ramp up, hold constant, ramp down, and then the subsequent ramp cycles. You see that nothing much changes, even if I give a 5-minute or 10-minute break. What that means is the internal structuration is extremely slow, right? It is not going to structurate from the inside. I have to help it. Otherwise, what will happen? A, I'm dealing with a Maxwell type fluid, which basically is going to continue to deform, and it's not building on the inside. So if I was to take one layer, put another layer on it, it'll just go, right? That's what is going to happen here. Right. So now the thing is, the rate at which the internal structure builds, I think this was introduced yesterday, we call it SRE, structural rate of equilibration. We do these experiments and measure the area under the ramp up, ramp down curve. And you find that, yes, the SRE does build up. But notice this here. This is basically whatever I measure as the SRE is the energy that would be required to shear off a structure. Where is that energy going? If a material structurates, it would basically take up more energy, right? What we are measuring here is a 0 point is after I smash the structure. So after I've done this, I wait for some time and then I do a ramp up, ramp down. So I get a curve like this and I measure the area in between this, which gives me the energy that is required to break the structure after it restructurates. What do I mean by that? Well, we go through this. I ramp it up to a certain rate, hold the rate constant, completely smash the structure, ramp it down, then hold it constant for some time, and then do a ramp up, ramp down. What I'm showing you here is the ramp up, ramp down data after I've done this here, where I've completely smashed the structure. Now, this area between this is basically the energy that would take to break the structure, which has been smashed. So it gives me an idea of restructuration that's happening inside the fluid, right? So this SRE that I measure with different time intervals. So this interval that I have here, if I increase, what's going to happen? I expect structuration to increase. So we measured the structuration in a mixture where I have fly ash and slag at 90 and 10 with 9% silica and 27% silica. What do you notice as the difference here? At 0, both are similar, which is basically where I am down. I wait for 5 minutes. This fellow doesn't structurate enough, whereas this fellow is structurating, right? If you look at 10 minutes, this fellow is still not structurating enough, but this fellow is, right? So if I was to print with this fellow with high silica content, what would happen? So remember, this stage here represents what's happening during pumping. When it's going through the pipe, when it's going through the nozzle, it's getting sheared very much. Then this is rest time that you have is the time that the layer is sitting idle before the next layer comes on. Now, before the next layer comes on, I expect that the structuration that's happening, that should be rapid enough that it can take the next layer on, isn't it? If I was to print with this fellow, what's happening? It's hardly structurating. So if I put the next layer on it, it'll simply lose its shape and even collapse. And that's and when does that behavior change? Look at the silica content. This is with a very low silica content. This is when I start increasing the silica content. Now the question is, then why not keep the silica content at low value? Strength. This is what gives me the higher strength. So I have to add silica for strength, but the minute I do it, I start losing structuration. Okay. Right. So this is what would happen. So 9% silica, 20% silica, 20% silica is showing you the Maxwell behavior. Look at this. Right? The 9% is showing a yield type behavior. This is what you get. Look, the layer definition with 9% silica looks okay. But if you look at it, when you look at the 20% silica, you see the layer deformation here. It's basically starting to spread out. And very soon, in fact, I have other pictures which I forgot to put here. You'd see that what starts out as a rectangular shape here, this is multiple layers, okay? It would basically turn into a pyramid. The bottom layers just start opening up. Right? So how do I help this fellow? I have problems, high viscosity, right? I can't do much about it. I just pray that my pump can take the pressure, right? But if I don't help it structure it, I have a problem, right? And where do I have problem with structuration? Wherever it starts getting into a Maxwell type behavior is where the structuration becomes a problem. When do I get into a Maxwell type behavior? When I add a lot of silica in it. Why do I need to add silica into the solution? For strength. So it's like a full circle, right? So remember the levers that we had when we were doing the concrete mix design? We had the basic things that I could control, right? But then we had these admixtures. That was my final lever, right? Can I put something in there that will help me with structuration? Well, what we found is that if we start adding clay in the material, okay, so what are we doing with clay? We are basically relying on the clay to give me the structure. Okay, what is clay? And I'm not adding clay to the extent of, say, producing LC3 cement. Small amount of clay. In fact, initially we started with nano clay and we were adding it at about 0.35%. What is the beauty of clay? Clay is a wonderfully thixotropic material. What do you expect when you deal with a clay slurry? Well, when you smash it, when you shear it off very fast, right, it basically, the structure breaks, right? Initially, you have big clumps of clay that come together. If you shear it fast enough, these will break up into individual particles, right? Then if you let it sit, what happens? Clay has a tendency to agglomerate. It will again form those clumps and start structurating on the inside. You can form these beautiful skeletons inside the solid. And that's what we're relying on this clay for. So adding a small amount of nano clay, look at what happened here. I had 0% silica, 6% of silica, right? I started seeing this Maxwell type behavior. Now, problem here, it's not structurating, it will not keep its shape. Just a little bit of nano clay, I start getting back my yield type behavior. The yield stress has increased like I wanted. And in fact, even the thixotropic measurements, which I'll show you in the next slide here, also start improving. This is also a measure of modulus, which I think Narayanan presented yesterday, which presents the stiffness of the material. Okay, why is stiffness important? It controls the deformation. So what happens when I add clay into this material? Well, my stiffness buildup happens much quicker and it's able to keep its shape. It doesn't deform that much. Okay. Now with that, then we were able to produce 3D printed concrete panels, okay, by controlling the rheology of the alkali activated binder. Okay, if you don't control the rheology, you run into one problem or the other. A few things that you can control, a few things you cannot control. So if you give me an alkali activated material which has sodium hydroxide and sodium silicate in it, expect it to be more viscous than cement paste. It will be. How much more viscous? By 2 orders of magnitude, which means it is going to be much more viscous than water. Why? Viscosity of water is 1 centipoise. Viscosity of an alkali activated paste is 1 at the very least, 1 poise, right? So big difference, huge difference. So you expect alkali activated concrete to be much more viscous. Okay, what is fundamentally more different is the way that this alkali activated binder paste would behave when you shear it. Now, what changes its behavior is all the silica that is present in the activating solution, right? Why do I need silica? I need silica to control my strength. Okay, if you are lucky and you're dealing with a source material which has highly reactive silica in a large content, then you don't have to bring in additional silica from the outside. Then you can just start working with this as if you're working with cement paste. Then half your problems are solved, right? But the minute you have to dose external silica, and usually that is brought in the form of sodium silicate. Okay. Now the question may be, some people do ask this: why sodium silicate? Why not nanosilica? Well, you could add nanosilica as well, except it's much more expensive. Water glass is much cheaper, and if you really want to scale up, nanosilica is not your alternative to be adding in that larger quantity, right? Whereas water glass is something that's available in large quantity. It's industrially produced, right? It goes into the making of soaps, so it's available, and you can source it in a large quantity, and you can think of scale up if you're going to do, and therefore sodium silicate is almost always used. Okay. We'll have to learn to deal with all the tricks that silica is going to throw at you. Silica will make the solution viscous, period. We are reducing the particle size. Yes. So if you look at the sodium silicate the viscosity graph, I think you probably missed it. So um, this one. So this is the graph of sodium silicate and viscosity. Okay. This is the MS, the silica to sodium ratio. If I take silica to sodium ratio, let's say to along this side where my sodium essentially goes down to 0, you'd see the viscosity would actually shoot up again. Okay. And when I'm dealing with pure silica, invariably you'll end up with this form here. It's going to be highly polymerized. Okay. Now, what sodium helps me do is also control the size of this silica particle in there. But that brings about a lot of complications. My variables, when I'm dealing with this, is much, much more complex. Okay. So, is there a one size fits all for alkali activated binders? No. Understand the rheology of the binder paste. How much silica content do you have in your solution? What is the MS, this ratio of the solution? Okay. And what is the solids to activating solution mass ratio? And understand that adding more silica will make the solution more viscous and likelihood chance of it becoming a Maxwell flow. If it becomes a Maxwell flow, good luck with the structuration. It's not going to structure it. It will not have an internal structure. It will just keep deforming, right? So which means that you have to bring in external additional agents to help it structure it, right? So what external agents would you use? Anything that structurates, right? And of course, you don't want to use anything that's expensive. So clays are our best friends. So initially, when we were doing this work, we were using nanoclay, highly purified nanoclay. But nanoclay is very expensive. Subsequently, we've done trials with regular bentonite, which we can order off of Amazon. We even use kaolinite, regular clays. And the beauty is all these clays tend to structure it. They stick together. That's how they hold water, right? So use that to our advantage to help this material structure it. Why is structuration important? If you don't let it structure it, as you put more weight on it, it's just going to deform and lose its shape, right? How long has the structuration to hold? It has to hold before the kinetic reaction kicks in, and then the material starts to harden because of the reaction. Then the reaction will take over, right? So whether it's a matter of a few hours, right, or a day, this structuration has to hold for that duration. How quickly should the structuration happen? Matter of seconds. Why? Because you smash the structure when you pump it, right? You subjecting it to high shear. What is the high shear doing? It's completely shearing off the material. Any floccules, etc., any structure that's there is sheared off. Then you deposit it. It comes to rest. And then before the next layer comes around, this fellow has to rebuild its structure inside. Okay. And so you need something that structures very quickly. How do I measure that? Thixotropy. I measure the thixotropic buildup that's available. Okay, the standard protocols that are available for thixotropic buildup. Of course, modifications have been done for the thixotropic buildup measurements, right? The most common measure is what I showed you as SRE, right? So what are you doing there? You're measuring the energy it takes to break the structure. So energy to break the structure when? Not the initial structure. The structure after you've sheared it off. You shear it off, you let it come to rest, and you rest it for different intervals of time. And then you measure how much of structuration has happened. More the structuration that happens after shearing off and rest period, higher energy would be required to shear it off. Okay. So, any questions? Today I promised Narayana I'll stick to time, so I'm going to stop here. Any questions? Like I said, a lot of literature on this, right? And I barely scratched the surface. So, any of you want any of this in detail, just write to us. We'll be happy to share our papers on this domain. Okay. Oh, sorry. Yeah. So the most expensive ingredients in, let's say, one of these alkali activated materials would be the sodium silicate and the sodium hydroxide, right? Now, if you look at just the cost of sodium hydroxide and sodium silicate, right, the cost works out lower. The biggest cost is usually the binder material. Okay, now, and that varies with the country. In India, we have plenty of fly ash. Okay, so for us, that cost almost goes to zero. Right now, it's starting to increase because the cement companies are starting to bid for fly ash. But if I say set that to zero, then it's a win-win. I'm only paying for sodium hydroxide, sodium silicate. The sodium silicate that I use doesn't have to be lab grade. It can be industry grade sodium silicate. So the costs actually come down significantly when you do that. Same with sodium hydroxide. Okay. I don't have the exact number, but yes, it does work out lower. Zeta potential is, suppose I give you, where was that? Yeah. So if I take a suspension of solids, let's say you take colloids, and colloids have a tendency to stick together. How do you determine that whether it will stay in a flocculated state or a separated state? There's a measure called a zeta potential. We measure, basically it's a measure of the surface charges on these particles. Loosely, I'm giving you a definition here. Now, if your zeta potential happens to be very negative, the particles will tend to repel each other. They will not stick together. It will be in a dispersed state. Yes, when the value of zeta potential is negative, it will stay in a highly dispersed state. So what have we done here? We've added silica to the solution, and then we've introduced the fly ash into the solution. So when we measured the zeta potential of fly ash and water is negative, right? The minute we added silica, it became even more negative. That means it's going to be highly dispersed, right? And it's going to be like individual particles. That's what silica does. It disperses them. It'll basically start, you'll start seeing these floccules form. It'll tend to agglomerate, clump up. The values near zero are what basically give you this the clumping. Usually we don't get into positive territory. Okay. Yeah. Beautiful question. Okay. Now, it depends on which binder you're using. Okay. If you are producing geopolymers, which is sodium aluminosilicate, which is called NaSH, unfortunately. If you're producing NaSH, it's all a game of alumina. The maximum strength you can get depends upon the alumina that is present. We don't even bother about the silica. Silica, we basically just manage the ratio of alumina to silica. Okay. If you're producing cash, okay, there alumina becomes like the poor second cousin. It's all a game of silica. Okay. So it depends on the binder that you're kind of producing. And what controls that is the ratio of fly ash to slag. If zero slag, I'm producing NaSH. Then it's all a game of alumina. Okay. And if it is 100% slag, it's all cash, no NaSH. Okay. Then it's all a game of silica that is primarily determining the strength. Cash is structurally very similar to CSH. Very similar. It has the same calcium backbone and silica tetrahedra that are attached to the silica with alumina kind of that breaks that chain. Okay. Any other questions? So now let me get to this question as well. So when we started doing our work on geopolymers, we found that everybody was using sodium hydroxide willy-nilly 8 molar, 14 molar. When we tried to mix that in our lab, my students complained that they were going blind because it is so pungent they couldn't even stand there. Then we started getting into why is it that we really need that higher molarity of sodium hydroxide, and we found that actually 3 molar sodium hydroxide is adequate. Why 3 molar? We've done the studies where we find that if you keep molarity of 3 and higher, the glassy phase of fly ash, that dissolves completely at about 3 molar concentration of sodium. You don't really need higher thing. So in all of our studies, we try to maintain 3 molar. We don't go higher than that. You can go higher than that, but that higher molarity is really not helping you. but you're paying for the sodium hydroxide, the excess that you're adding in there. If you keep it around 3, it's adequate. Your glass will dissolve. You'll get your Nash formation happening. Okay. Now, when you're talking about slag only, right? There, in fact, you don't even need a high molarity. It'll react even in water. It's a little slow. So what does the sodium hydroxide do? It basically kickstarts the dissolution. You get a faster dissolution and hence a faster reaction in there. Okay. You'll have to establish how reactive is your silica in these materials. If it is sitting in a glassy form that is not very reactive, yes, you'll have to go higher in pH or higher in molarity, not pH. Okay. Right? Yes. What's your opinion on the transportation has yeah, this is always an issue. I mean, there are always naysayers. So if you pitch something, they'll say, "Oh yes, but." So there are always issues with all of these materials. Now, one thing that people say is, how do you transport the alkalins? Where do you store them? How do I mix them? Is it not unsafe because it's highly caustic and this and that? Yes. Now, the solution for that is what I presented overall here is what we typically call a two-part geopolymer, where they're mixed separately. The solution is mixed separately, the binder is brought, and then we mix it. But now we are trying to see if we can develop one-part geopolymer, where basically this geopolymer powder comes in a bag, where we pre-blend sodium hydroxide in a powder form, pre-blend sodium silicate, which is also in a basically solid form as a metasilicate, and then all you do is add water. So then the process is no different from cement paste, except it's much more alkaline, right? So it's like any other industrial product then, right? One way the thing is micrometer versus microscale nanoscale, because the size is small, we expect the larger surface area. Yes. We expect it to go. Except if you look at this, right? It's a game of this. So while it's on the nanoscale, if they're highly dispersed, what structuration? They're not going to come together. So you want them to come together. Okay. And that's where, if I start adding silica, that's precisely the point. While these particles are on the nanoscale, they are basically all sitting separately. They're not structurating. Okay. And this is the problem I face. So what we said is, look, I'm not even going to worry about this. What will I do? I'll bring in additional material which loves to structure it, which is the clays that we brought in. This can happen extrusion also, where we extrude this image sample. That's right. So if we do this, right, if I try to get this fellow to structure it, so this is fly ash sitting in a sodium hydroxide, sodium silicate solution, right? And the particles are just sitting separate. They won't come together. They won't structure it, which means what? If you actually extrude, it'll just spread out. That means I cannot rely on this fellow to structure it, right? So you have to bring in another material which loves to structure it and gets them to stick together. And that's where we brought in the clay to help us out with the structuration. Okay. Yes. Oh, yeah. So silica content, remember when we talked about packing, right? Go back to your our basic definition of the concrete. Where was that? Yeah, this one, right? Silica is sitting here. Packing is happening here. Two very separate scales, isn't it? Okay. So packing, I'm worried about here. Once I get into concrete, this fellow. And yesterday we spent a lot of time on this. Today I focused on this. Okay. And the impact of this on this, which is the concrete. Okay. Of what? Packing efficiency is not affected by this, right? It's like two independent probabilities, right? This fellow doesn't know what this fellow is doing unless they come together. Okay, so the packing efficiency is controlled by what you give me as aggregate. I'll play around with that and get you a nice packing efficiency. Okay, at this scale of divide. Okay, so, and this fellow doesn't know what is coming here, but they come together here and then it starts behaving like a composite material, the concrete that we know. Okay. Can we Yes, at some level we can. Because remember the viscosity graph, it goes through a U-shaped curve. So where it is highly in a mono form, although that is more of a chemical bridging that's happening, if it's highly dispersed, the viscosity would be high again. Okay. A higher viscosity. Okay. Yes, but why would you? You can, but why would you? I mean, you can, but then the whole chemistry changes, right? So typically we don't bring in. There are a few people who are looking at, again, if you are after cash, then perhaps cement may help. But if I'm after Nash, why would I want to add cement? It'll completely ruin my chemistry. Okay. All right. So I'm going to stop here.